Hi, Gretel. So in this video, we're going to be determining the equation of a tangent to a curve. So the curve can be a quadratic function or can be a cubic function. This is also part of differential calculus. And this is one of the questions that are very popular for exams. So before I determine the equation of the tangent to this curve that we have here, I'm going to first explain one of the most important principles. So we're going to use the idea of the derivative of a function in order for us to get the equation of the tangent. So we've got two things here. We've got the curve and we've got the straight line, which is our tangent. So before I determine this equation, I would like to indicate that each and every student must know that the derivative of a function means the gradient of that particular function at any x value. So I need you to know this. So it's an NB here. NB. So the derivative is the same as the gradient of the function at any x value. So this means that when you're given the function as f of x, the derivative of that function means that you are calculating the gradient of the function at any x value, right? So that's what you must note. Number two, you must note that the curve and the tangent, they have equal gradients at the point of contact. That's point number two. Number one there. Number two, we're saying the curve gradient, so the curve gradient, so that's going to be m of the curve is equals to the tangent, so it's equals to the gradient of the tangent. So the curve and the tangent, they have equal gradients, so I'm going to call this m10, m of the tangent. So the gradient of the curve and the gradient of the tangent are equal at the point of contact. So the point of contact, so here, are equal at the point of contact. So the point of contact, it's the point where the straight line touches the curve. So what we're saying is that the gradient of the curve and the gradient of the tangent are equal at x equals to 5/2. These two functions, they have equal gradients because they meet at x value, which is 5/2. So we're going to use these two most important points to determine the equation of the gradient of the tangent to the curve. So basically, what we need to do to get the equation of the tangent, which is a straight line. Remember, the tangent is a straight line. So for us to get the equation of a straight line, we must first get the gradient of that particular straight line. And how are we going to get the gradient of the straight line? We're going to use the gradient of the curve at x equals to 5/2. Because the gradient of the curve at x equals to 5/2 will be equal to the gradient of the tangent. So that's what you must always think of. The main question here is to determine the equation of the tangent. And if the main question is to determine the equation of the tangent, then now you ask yourself, what is it that you need to get the equation of the tangent? To get the equation of the tangent, you need to know the gradient of the tangent. And how do you get the gradient of the tangent? You use the gradient of the curve. That's that. Okay, so here, because we need to know the equation of the tangent, we need to get the gradient of the tangent. So we're going to get the gradient of the curve. Remember, our curve there is given by f of x. So our curve, remember, is f of x equals to x squared minus 4x plus a 3. So what we're going to do here, we're going to get the gradient of the curve. So what is the gradient of the curve? Remember, we said that the gradient of the curve is the derivative, the first derivative. So because we have got f of x, so we're going to get the gradient of the curve as f prime x, and then we're going to use the power rule. So the derivative of x squared minus 4x plus a 3 will give us 2x minus a 4. So this is the derivative of the function of f of x. But we know now that the derivative is the gradient of the function at any x value. But we're not looking for the gradient of the function at any x value. We are specifically looking for the gradient of the function at the point of contact. What is the point of contact? Remember, the point of contact is 5 over 2 is to negative 3 over 4. So it's to negative 3 over 4. So don't lose this thing. We have the gradient of the curve at any point, which is 2x minus a 4. But we want to know what is the gradient of the curve at x value equals to 5 over 2. So to get the gradient of the curve at the point of contact, it means that we're going to substitute the x value to the gradient at any point. So this is going to be f prime 5 over 2. So anywhere where there is x, we're going to substitute 5 over 2. This is going to be 5 over 2 and then minus a 4. So this will give us an answer of 6. So what we're saying is that the gradient of the curve at the point of contact is 6. So the curve has got a gradient of 6 at the point of contact. But remember, we're not looking for the gradient of the curve. We're interested in the gradient of the tangent. So which principle are we going to use now? We're going to use the principle that the curve and the tangent have got equal gradients at the point of the curve, or at the point of contact. So this means that if the gradient of the curve at 5 over 2 is 6, therefore the gradient of the tangent, therefore the gradient of the tangent will also be equals to a 6. And why is it 6? Because the curve and the tangent have got equal gradients at the point of contact. So basically, that's what you use to get the gradient of the tangent. So we have the gradient of the tangent. When we've got the gradient of the tangent, to get the equation of the tangent, we're going to substitute the point of contact. The point of contact, remember, it's 5 over 2 minus 3 over 4. So we're going to use this equation to determine the equation of the straight line. So we're going to have y minus y1 equals to x equals to m, which is the gradient, x minus x1. So y1 and x1, it's a point in the Cartesian plane that we're going to substitute. So we're going to substitute the point of contact because that's the given point of the tangent. So when there is y1, we're going to substitute the y value. So this will be y minus 3 over 4. Then the gradient of the tangent is 6 because we calculated it using the gradient of the curve into x minus the x value is going to be 5 over 2. Then now we're going to simplify this particular stuff there, and then we're going to get on the right hand side of the equation, we're going to have 6x minus 15 into, and then on the left hand side, we're going to have y negative times negative 3 over 4. It's going to be plus 3 over 4. And then what we're going to do there is that we're going to carry over the 3 over 4 to the other side. And when we carry it over to the other side, we're going to get y equals to 6x minus 57 over 4. That is the equation of the tangent that particular curve over 4. So this is very simple. You must always use these two principles to get the equation of the tangent to the curve. So what I want you to do here, I need you to try one example where you have got a cubic function and you try to get the equation of a tangent to that particular cube function following the same steps. Remember, you must get the derivative of that function, and then you get the gradient of that particular curve at the point of contact. And whatever value that you're going to get, you need to equate it to the gradient of the tangents because they're always equal. And from there, you need to substitute the point of contact to the equation that we use to determine the equations of the straight line.